our lecture video for January 21st. Let's get started with a review problem. This is what we were talking about the last few classes, is how to solve a problem like this. So copy down, maybe pause the video, attempt it yourself. And what we want to do is we got to get n by itself. The hardest part of that is getting rid of this rational exponent, but we have a trick. We can raise both sides to the reciprocal of this 4/3, which would be 3/4. And when you raise an exponent to an exponent, you multiply those exponents. So these would actually multiply and become a 1. So all that's left on this side is just 64n equals 256 to the 3/4. All right, we could plug this into our calculator, but let's pretend like we don't have our calculator. Let's see if we can evaluate this by hand. This here would be the same as the 4th root of 256 to the 3rd equals 64n. And now, is 256 a perfect power of 4? So maybe you've got these written down, but 4 to the 4th equals 254. So 4 to the 4th equals 256. So if that can be rewritten as a 4 to the 4th, the 4th root and the to the 4th would cancel out, and I would just have 4 cubed equals 64n. 4 cubed can be computed, that is a 64, so 64 equals 64n. Divide both sides by 64, and we get 1 equals n, or n equals 1. All right, plug it back in to double check. Here maybe we will use our calculator. Is 64 to the power of 4 over 3, make sure that all stays up in the exponent, equal to 256? It is. All right, goal for today is to learn how to do operations of functions and composition of functions. Why functions are like mathematical machines, and machines can be combined to make better machines. I would also say this is the closest link between algebra and coding, is when we start talking about functions. All right, question for you. You want to buy a sofa. You have 2 coupons with you, and the store will allow you to use both of them. One coupon will take $50 off the price, and the other will take 5% off the price. In which order should you apply the savings to save the most? How much better is it? Or is it the same? Does it not matter what order you hand them over and have the discount applied? So I'll bet a question here for you to try that out and tell me. Okay, so we'll say the couch costs X. So X equals the cost of the couch. And now when we take $50 off, that's really easy. We just subtract 50. So if I apply that first, I'm going to just subtract 50. When I take 5% off, a lot of people do this wrong, and they just get what 5% of this is. But you have to realize when you take 5% off, you still have to pay for 95% of the couch. So you multiply by what's remaining. All right, so by writing an equation like this, I'll take the $50 off first, then I'll apply the 5% savings. All right, I need to distribute the 0.95 here. I get 0.95x minus, and then 50 times 0.95 is minus 47.5. Like a 0. All right, so that would be an expression for the final cost of the couch. All right, let's do it in the other order. Let's apply that 0.95 first, so 0.95 will get applied to the price first. Then we'll subtract away the 50, so really just different spots of the parentheses. And this can't be simplified any further. And now let's compare these two. So in this scenario, we save 5% and then an additional $47.5. In this scenario, we save 5% and then an additional $50. So this is our winner. Because 50 is more than 47.5, we want to do the 5% first, and then the $50 off second. And I think I find it interesting that it doesn't actually depend on the cost of the couch how much better this second option would be. It's always going to be $2.50 better. regardless of the original price of the couch. And this should make a lot of sense. We want to take the 5% off of the bigger amount because that 50 is fixed. So take the 5% first off the bigger amount, then the fixed 50, versus the 50 first, then the 5% off the smaller amount. All right. So what we're doing here, we could think of these coupons as functions that act on the price of the couch, that take the price of the couch and modify it to be some new price. So that's a really good way to think of functions, is like a coupon. What makes a function different from an equation? Well, here we have an equation with a y equals. Here I have a function, and we say this as f of x. And the strength here is that we keep track of the input. So it keeps track of the input. So if I plug in a value for x, it'll come in here and here. Over here, if I plug in a number for x, it'll get multiplied by the 2 and then added to 3, and the value of x will disappear. It will just sort of meld into this 2 and this 3. So it keeps track of the input is a big feature of function notation. But it does have some limitations. It's much harder to do inverse operations with a function. A function really is just an expression tied to some function. All right, although you could do stuff like subtract 3 from both sides, divide both sides by 2, it gets a lot messier with functions. Well, this is better for inverse operations. Or especially if you want to have multiple terms on both sides, it could be rearranged into a function generally, but can get really messy with that f of x versus just the single variable y. Okay. Function operations. So functions are mathematical machines that take inputs and give you outputs. You can combine functions by running them on the same input. So this is your input here. And then combining the results with some sort of operation. All right, and it's exactly how you would think it would work. F plus g of x is f of x plus g of x. We just write the input only once. So I think better than writing all these down, although you should write all those down, is to show that f plus g of x does this. It takes some input x, all right, it duplicates it, and it passes it through f of x and g of x. All right, these both give us a number, and then it adds those numbers together to get some final result. So input, duplicates it, runs it through both of them, adds the result. And then whatever operation we see here is how it combines the results. We could divide the results, multiply the results, and we get some sort of final result. And we would actually call that result f plus g of x. That number is f plus g of x. A little better plus there. Okay, and so we'll just say result. All right, so this whole thing is called operations with functions. Let's practice adding and subtracting some functions. When we define functions, we normally start with this word let. It helps define the functions. A lot of programming uses this word let to indicate that you're going to define a function. And a lot of proofs in math use that as well. All right, so f of x equals 4x plus 7, g of x equals x plus 1. Find f plus g of x. Well, this is the same as just doing f of x plus g of x. I'll substitute in their properties. 4x plus 7 plus x plus 1, and we get 5x plus 8. So f plus g of x equals 5x plus 8. It's still an expression. It's not a number because our input is still just the variable x. F minus g of x. Well, that's let's shortcut it. That's going to be 4x plus 7 minus, keep this in parentheses, x plus 1. Distribute the negative here, and we get 4x plus 7 minus x minus 1 equals 3x plus 6. All right, now let's actually evaluate a function. Let's do f plus g of 7. So instead of running both, I'll run it through the combined expression. So this would be 5 times 7 plus 8, which equals 35 plus 8, which equals 43. All right, multiplying and dividing functions together. Again, we got 2 more defined. F times g of x. So I need to take the expression for f of x and multiply it by the expression for g of x. And here, we can get a pretty big polynomial. We're already starting with a quadratic, and then we bring in more variables. So keep parentheses here, x squared minus 9. Let's parentheses here, x plus 3. And then we will FOIL this. And we get x cubed plus 3x squared minus 9x minus 27. And no more like terms. F divided by g of x. So I'll write it down, f of x over g of x equals x squared minus 9 divided by x plus 3. Well, when you see that x squared minus 9, a little alarm bell should be going off in your head, because this can be factored into 2 conjugates whenever you've got a negative perfect square there. So x plus 3 times x minus 3 all over x plus 3. And you can FOIL the top there to convince yourself that that is equal to x squared minus 9. Now let's cross out the x plus 3, and we're left with just x minus 3. But we need to remember, although we canceled out the bottom, this could still cause some discontinuities. It could cause a hole in our function. So we have to say that x cannot equal negative 3. If x was equal to negative 3, in the original running of the functions, g of x would be equal to 0, and then you're trying to divide by 0, and it's not good when you try to divide by 0. All right, on to composition of functions. So this is where a lot of people get confused, but it's really not that confusing. Sometimes this symbol throws people off. G, we say this as of f of x. So this is f of x, and then it's g of f of x. All you have to remember is to run these backwards. All right, and a picture can be really helpful here. What this means is evaluate f of x first, then use f of x as the input for g of x. So we've got some input x. We might plug in a number, we might plug in an expression. This is our input. Instead of duplicating it and running it through g of x and f of x separately, we just only run it through f of x. The first mathematical machine. That would give us some number. We call that number f of x, but it's just a number. We take that number, and then that is now the new input for g of x, which gives us then our final output, g of f of x. And we write it like that because f of x got ran first. So you can't even run g of x because you don't know what its input is. Its input is f of x. And that's our output. So the vocab words you could use for this is that with composition, the functions are run in series. With operations, they're run in parallel. All right, so let's define some new functions, a new f of x and a new g of x. F of x equals x minus 5, and g of x equals x squared. Can we find f of g of negative 3? So remember, we run these backwards. Negative 3 goes to g first. That output then goes to f. So I'm going to take negative 3. I'm going to plug it into g of x. G of x is a function that just takes the input and squares it. So negative 3 squared becomes a 9. That 9 I'm then going to run into f of x. F of x is a function that takes the input and subtracts 5. So now we've got 4. F of g of negative 3 equals 4. All right, g of f of negative 3. So same input, but we're going to run it in the opposite order. Maybe we'll get the same answer, maybe we won't. So -3 goes into f of x, which chops off 5, so we now write down at -9, which then goes to g of x, which squares the input, and we get 81. So very different answers when you do f of g of -3 and g of f of -3. All right, f of -3. So let's write this down how we actually should write this down. So what we should do is plug -3 in for the input in f of x, put a set of parentheses around that, and then take that whole unit and plug it in for x again. So you can compose functions with themselves. It's totally fine. And that just means, again, another 5 is taken away. If you run the function that takes away 5 twice, you'll end up taking away 10. And this here equals -13. All right, and g of f of x, now we just have the variable there, so we're going to take an expression for f of x minus 5, plug it in for g, which squares the input, so we'll put a little squared there, and this becomes an x squared minus 10x plus 25 if it's all the way simplified. All right. Inverse of a function. So the notation is a little -1 here. All right. This is how we say this. The inverse of f of x. And an inverse will exactly undo operations done in an original function. If one function adds 3 to a number, then adds 2, the inverse will then subtract 2 and then subtract 3. And we'll just run it the opposite. So I'll write this down. It's opposite operations in the opposite order. And we can see if we start with some input x and we run it through f of x and then run the result through the inverse of f of x, we'll get a matching output. So this will be a matching output. All right. Find the inverse of the following equation. So here's a trick to find the inverse super quick. You just swap x and y. So you swap x and y. And this totally inverts the function. The output, which sometimes we call y, becomes the input, and the input becomes the output. So now we've got x equals 3y plus 7. Technically speaking, we have found the inverse. We are done. But we never write our equations as x equals. We got to get this y by itself. So now you go to work isolating that y, and we get x minus 7 equals 3y. Divide both sides by 3. And we get y equals x minus 7 over 3. And this should make sense. This original function, we could call this a function, even though it's a y equals on the other side, multiplies the input by 3 and then adds 7. If we reverse that, we would subtract 7 and then divide by 3, which is exactly what this does over here. All right, so let f of x equal the square root of x minus 2. Find the inverse. So one thing I'm going to do is I'm going to replace f of x with a y. This is another utility of the y equals. Rewrite this as y equals the square root of x minus 2. And then I'm going to swap x and y. X equals the square root of y minus 2. Now we got to get y by itself, so I'm going to square both sides. And I'll get x squared equals y minus 2. I'll add 2 to both sides. And I'll get x squared plus 2 equals y. Now I get rid of that y, and I can rewrite it as f to the -1, or the inverse of f of x, equals x squared plus 2. So one more time, rewrite the f of x with a y, swap the x and y, solve for y, now rewrite with a f to the -1 of x. All right, how can you use composition of functions to verify two functions are inverses? Well, if you compose a function with its inverse, what should you get? you should just get an x, because the input should match the output if you run a function and its inverse in series like that. All right, I'll embed a few more questions for you here, but that's that for this lecture video. Have a great rest of your day.